the derivative being 0. Now, we want to know where the derivative doesn't exist. Oh, we didn't talk about domain. I should talk about domain. Are there any domain restrictions here? No, because cosine is defined everywhere. X is defined everywhere. You add them together. Domain of this is everything, right? Okay, so we got that. Where's the derivative not exist? Well, here's my derivative, right? Does that ever have any problems? Does that derivative ever have any problems? No. You can plug anything into that. You don't have division by 0, right? This is good. So you don't have anything to worry about here. Excuse me?
Oh, it's because you wrote F double prime.
Oh, did I put, I'm sorry, I did put double prime. Thank you. All right, now what?
Now you draw a number.
You draw a number line. You draw a number line. And that means you're going to have to put your critical numbers. How many critical numbers do we have?
Infinite.
Infinitely many of them. How are we going to do this? Well, we can do pi over 2, right? That's one of them for sure. What's another one? What happens if you add 2 pi to that?
3 pi.
You get... So if k is 1, you're adding 2 pi. You get a common denominator. 5 pi over 2. 5 pi over 2 would be the next one. What would be the next one? What do you got? 9 pi over 2. What we're doing here is we're just replacing k with 1, then 2, then 3, and then combining with the common denominator. And that keeps going, right? You can kind of see the pattern, right? This is 1 pi over 2, then 5 of them, then 9. Next one should be 13 pi. Do you see it's growing by 4 each time on top? And that goes forever, right? And it goes the other direction as well, right? Doesn't it go the other direction? All right. Let's see what the hell's going on here. I need to pick a test point. Let me do one more to the left of this. What would the one to the left of this be? Negative 3 pi over 2. So you're subtracting 4 from this on top. All right, let's pick some test points. Here, 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 here. Right? Let's just do a couple. And I think we're going to see a pattern in this. What would be a good number? Let's start with that one right there. What's a good number between pi over 2 and 5 pi over 2? That means you can go anywhere between here and all the way back around. Any angle you want from here all the way back around. What's a good angle between here and all the way back around? You could do pi. You could do 2 pi, right? Probably pi or 2 pi would be good, yes? What do y'all want, pi? Where are we plugging it in? Yeah, let's put them here first, sorry. This would be pi. That's going to be a test point. What's another test point? Between here and here. Pardon me? 3 pi. Could you use 3 pi? What is this? This is like... You can do 4 pi. It's anything you can come up with between those, right? So you could look at it this way, like, what's 5 divided by 2? 2.5, and this is 9 divided by 2, which is 4.5. Anything between 2.5 pi and 4.5 pi. 3 pi, 4 pi, right? Whatever you want. So what do y'all want? 3 pi? And then something between 4.5 pi and, what's this, 6.5 pi? 5 pi. See, we're just adding what? 2 pi to each of these? Okay, so that's up to you. Negative pi over here. All right, all those test points go into the derivative, right? The first derivative, which was right here. And we're going to have the same answer for every single one of those. What happens when you plug pi in sine? What's sine of pi? 0. What's sine of 3 pi?
0.
Sine of 5 pi? 0, 0. All of those are 0, aren't they? So 1 minus 0 would be 1. So do y'all see if we plug any of these in to the derivative, we get a positive answer. So our derivative is positive here, derivative is positive here, derivative is positive here, derivative is positive here, which means that this function is increasing, 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 and never decreasing, is it? That pattern would continue. So the function just keeps going up, 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 up. We can answer the first 3 questions. Where's it going up? Everywhere. Where's it going down?
Everywhere.
No. Nowhere, right? How do we say that? I talked about this last class. Everywhere would be negative infinity to infinity. Where would nowhere be?
Null set.
Yep, empty set or null set. You can say null set. And then, do we have a local max min?
No.
No, because we never go up, and down, and we never go down and up, right? So we have none. None. Questions? Yes?
I'm confused.
Okay.
Doesn't the sine function do this?
Yeah. Yeah. The sine function oscillates. Yes, it does. But this doesn't because of the x in front. That's what causes this to not. Now, it's going to do something, but it's never going to do this. It's almost like a staircase. We'll see. We're going to graph it. It's pretty cool. All right. So this graph always goes up. All right. Now let's do the same thing for the second derivative. Oh, did we ever talk about where it doesn't exist? Oh, we did. We did.
Yeah.
Okay. So we got everything. Boom. All right. We're going to do everything now for the second derivative. Right? Everything again, second derivative this time. And the second derivative is super nice, right? Second derivative, let's set it equal to 0. And that's negative cosine x equals 0. So where is cosine 0? Go to your unit circle. Cosine is the x-coordinate. Here and here, right? It's not pi over 2, just pi over 2. It's pi over 2 and then also 3 pi over 2, right? You can set up 2 sets of solutions, or you can do this. You can say, all right, x has to be pi over 2, plus, to get to another answer, you add a half revolution, pi k. Now look, if this is confusing you, what I'm doing here, that's okay. It's normal for students to be confused here, because this is from pre-cal. All right, so if you need some refresh on this, get with me. I'll be happy to go over that with you. For now, let's just put it down and continue. All right, so I'm gonna draw. Is this ever not defined? Is the second derivative ever not exist? No, no problems, right? It's just a cosine function. Exists everywhere. So I'm going to put down here, let's start with pi over 2. And then the next answer was 3 pi over 2. What do you think the next one's going to be? 5 pi over 2. Then 7 pi over 2. And then 9 pi over 2, and they keep going, yes? And we go backwards also. This would be negative pi over 2. And that breaks up my number line. And then I've got to pick something in between these. You've got 0, right? 0's in here, right in the middle of these. And then what would be this one, right in the middle of those? Pi, right? Between pi over 2 and 3 pi over 2, right in between those two is pi. And then between this one and that one is 2 pi. And it just keeps growing by pi each time. And what happens if I plug any of those into the second derivative? Here's my second derivative. Plug 0 into this. What's cosine of 0? 1, and then times negative. Negative 1. So no matter what I plug in, I'm always going to get a negative second derivative, right? So my second derivative here will be negative for all of these, right? And what does that tell me about my original function? What is it doing? Concave, down. Pardon? Oh, yeah, no, I messed up. You're right. Sorry. It's not. At 0, this is what, 1? But at pi, what is that? -1, and then put a negative. So it's going to switch. My fault. This is positive at pi, which means we're concave up. And then we're concave down, and then back to concave up, right? And so on and so forth, concave down. So at 0, we get a 1 there, right? Cosine of 0 is 1, then make it negative, so that's negative. And then when we go to pi, cosine of pi is -1, times -1 is +1, so it switches. And it'll just keep doing that. Yeah, how do we write this answer, right? So here's how we would write the answer. Where's this concave up? Let's talk about that first. So I'm ready to answer these questions. Where is it concave up? Well, by looking at it, let me highlight it in red. Aren't we concave up like right here, and then again right here, and then again right there? It keeps on jumping, right? Yes?
If you like, it's pi half plus 2 pi k, and then you do that like the interval.
In the interval, yeah, we're going to use the same thing. So let's just look at this interval right here. This interval right here is pi over 2, and then 3 pi over 2, right? That would cover this, wouldn't it? The next one we want it to be what? 5 pi over 2, comma 7 pi over 2. And the next one would be 9 pi over 2 and 11 pi over 2. So the way I can write that is this. I can go pi over 2, I'm going to leave a space, comma 3 pi over 2. And then how much do you jump by to go from here to here? 2 pi, right? From here to here, you add 2 pi. And then from here to here, you add 2 pi. So what I can do is just put plus 2 pi k, 2 pi k, comma 3 pi over 2 plus 2 pi k. So if you give me a value of k now, like if k is 0, it kills that and gives you that first interval. If you plug in k as 1 here and here, you get the second interval. Plug in k as 2, you get the third interval, and so on and so forth. Does that make sense?
So you don't continue writing.
No, because this k covers all of them.
Yeah.
That's where it would be increasing. And then decreasing would be the same principle, yes?
Don't you have to state that k is an interval?
We're going to just assume at this point you understand that. I mean, technically you should state k is an integer, right? But without loss of generality, that's a math term we like to use. Without loss of generality, basically meaning like as long as we all know like where k came from, we're good, right? All right, so now where's it going down? Well, that would be, yeah, we can start here. We can start anywhere you want. You want to do this one? 3 pi over 2 plus 2 pi k again. And then the end point of that, or the end of that, is 5 pi over 2 plus 2 pi k. Does that answer your question? How we'd write that? Okay. So yeah, I guess I'll be precise just since you brought it up. I will add on to the end of this. K is an element of Z. So K is an element of Z. I mean, Z, this double struct Z, you know how we have double struct R means all real numbers? This double struct Z means the integers. Yes?
Why does that have to be double struct? Why not just?
That's just the notation. That's just what most notation is used. The double struct represents that group of numbers. We have double struct R for real numbers. Double struct N is the natural numbers. Double struct Z is the integers. Double struct Q is all rational numbers. Double struct C is the complex numbers. It's just a standard convention we use for representing sets of numbers.
What's the E?
The what? E is just a number. So E is not a, these are all sets of numbers, right? This is all your real numbers, all your natural numbers, all your integers, all your rational numbers. E is just one number that lives, actually, where does E live? Only in R and C. It lives in both of these. So I don't know if that, yeah? Okay, we've answered these two. Do we have any inflection points? Infinitely many inflection points. Actually, every one of these is an inflection point, isn't it? Every single one of those is an inflection point. So what we could do is just list how we got these. Do you remember? We had a formula to get this, didn't we?
Pi over 2 plus pi k.
It was pi over 2 plus pi k, right? Not 2 pi k. So to answer this would be x is pi over 2 plus pi k instead of 2 pi k. That's where we have inflection points. All right, I'm going to graph this because I think it's worth us looking at. So let's do, what is it, x plus cosine x. Let me go to the standard graph because that looks weird. There we go. Yeah, that's good enough. You see that function? See what it's doing? Right? Always increasing, right? But you've got all these little inflection points where you go from a frown, right, to a smile, back to a frown, back to a smile, back to a frown, back to a smile, back to a frown, back to a smile. See that? So before computers, people had to put all these ideas together to draw these things very accurately. It was a real pain in the ass, all right? Okay, it's 2:30. Let's take a break, all right? And we'll come back and we'll pick up, all right? It's a good place to stop. Yes? All right, I said 2:45, right? So we'll continue. All right, I want to show you two things before we move on, all right? Two things. The first thing I'm going to show you is something that we already talked about earlier a couple of days ago in this class that had to do with the quadratic parabola and the vertex formula. Remember that, H and K? We're going to talk about that first. And then after I do that, we're going to do one problem where we take a function and we sketch it. Now, I'm not going to test you on that, but it would not be, I would not feel right as a, calculus 1